So take a look at this weird text. Does anybody recognize this? Okay, now take a look at this text. Do you recognize this? Right? It's the Hippocratic Oath. So in order to do this task, you had to do two critical things. You had to decode and you had to comprehend. If the second task was easy for you, it puts you over here in the realm of a typical reader. Now take a look again at this first text. It turns out this is written in this weird phonetic code, and I'm going to give you a few clues to help you figure out how to read it. So look at these symbols. That's an A and an I, and in this alphabet, or this code, that makes the sound I. So I'm going to show you this picture to help you remember that. Now look at these weird symbols. Together they blend to make the sound air. It's hard for me to show you a picture of air, so instead I'm just going to write the word in red, and that should help you remember it. Are you starting to see it? So this is what it's like for our patients with dyslexia. They have trouble decoding the signal that's in front of them. They can comprehend it once they have it. But this is the fundamental difference between normal reading and dyslexia. So dyslexics are by definition incredibly bright. They love to listen to stories and they understand everything that they hear. But they can't map sounds to symbols. And so it's hard for them when they look at this to remember that that's a magic E at the end of that word who makes that vowel say his own name, and they can't figure out, does that say hate or does that say hat? Dyslexia is highly heritable. It runs in families. The prevalence is between 5 and 17%. That means in a regular sized classroom, 2 to 3 children will have dyslexia. So most kids in first grade learn to read just fine and they go on to graduate. But if you are in first grade and you have trouble learning to read, you have a 75% chance of being a poor reader in high school. And that puts you on a path for increased risk for a lot of things, for alcoholism, school failure, depression, anxiety, and unemployment. What do we know about dyslexia from neuroscience? In our classic fMRI paradigm, we ask people to go in the scanner and look at words and read them. And when we look at typical readers in the scanner, we see this regular network. When we look at dyslexics in the scanner, we see this. We see underactivation of these posterior regions, and in fact, they overactivate a region on the right hemisphere. So there's this interesting fact, right? When we look in classrooms, we know that there should be 1 in 10 children who have dyslexia. But when we look in classrooms in inner cities, in classrooms with children from low SES backgrounds, it turns out the rates are as high as 8 in 10 children. So what's going on? It's not mathematically possible that this is genetic dyslexia. Something else has to be happening. So Kim Noble did this really interesting experiment. And she used the classic MRI paradigm, showed children words, and asked them to read. And she recruited poor readers. She recruited them from high SES and low SES backgrounds. When she looked at the children from high SES backgrounds, she saw exactly what you would think you would see. They looked like classic dyslexics. When she looked at brain activation in children from low SES backgrounds, it was totally different because all of our prior research came from children from high SES backgrounds. So when she looked at the low SES background children, she saw that their pattern of activation was different from the children from high SES. And in fact, it looked pretty much like a normal reading brain. But these children still can't read. So what could be going on? Maybe it's comprehension. So we did this follow-up experiment where we used a different MRI task. And instead of just showing children words in the scanner to measure decoding, we also played spoken words to measure comprehension. So children are shown a visual image like a dress, and then they have to make a response to indicate if a word that they see or hear matches the image on the screen. If it's only a reading problem, then you should only see differences in response to visual stimuli. So in this experiment, we looked at poor readers from low SES and 2 key networks, and we looked at activation to print and then activation to speech. When we looked at activation to print, we found again, like Kim Noble saw, normal activation in the left hemisphere. But remember, these kids still can't read. So when we looked at activation to speech, it's where we saw something different. This is activation in the right hemisphere, which is on the wrong side of the brain. They should be activating on the left hemisphere. So we suspect that poor readers from low SES backgrounds have problems in the comprehension circuit and not in the decoding circuit. We had a second hypothesis, and this was that there could be environmental causes contributing to reading problems that we see in these children from low SES backgrounds. We know that early life exposure to lots of things like air pollution, lead, tobacco are associated with reading problems. And maybe this is because children from low SES are differentially exposed to these things. One such neurotoxicant is PBDE. These are flame retardants, and we study them in our group. They're ubiquitous. Ironically, we use them to keep us safe from fire, but it turns out they may actually be endangering our children. We've been looking at what happens to the reading brain with greater PBDE exposure. On the x-axis, you're seeing concentration of PBDE in maternal blood serum in the first trimester of pregnancy. On the y-axis, I'm showing you this relatively new thing called global efficiency. This is effectively how well the reading circuit is working as measured by fMRI. Okay, so these are data from 33 5-year-old children selected from a prospective longitudinal cohort study. And what you see is that the higher the concentration of PBDE, the worse the reading circuit is working, the lower the global efficiency. So increased exposure to chemicals in the environment is another way that children from low SES backgrounds may have unique reading problems. Okay, so there are a lot of sick children, and the real question here is how do we treat them? Currently, the standard of care is something called Orton-Gillingham, which is a fantastically cutting-edge treatment for teaching kids to read. It's actually that thing I did with you earlier today. Do you remember I showed you these pictures to help you remember the sounds? That's the state of the field. That's Orton-Gillingham. It was developed in the 1920s. So we can do better to help dyslexic children than use a treatment that we developed 100 years ago, but that's a story for another day. The other piece, and I get this question all the time, is who cares about any of this neuroscience research? What functional implication can it have if you're treating children? And here's the answer. Our neuroscience research today shows us that while we've diagnosed all of these kids with dyslexia, they're not all the same. For the kids in the top left, we have to do the standard or better. But for the kids in the bottom, if the problem is one of comprehension, then we need a different set of interventions. For example, we need to make sure that there are books in the homes of young children, like the new Reach Out and Read initiative in New York City. And we also need to make sure that preschools have vocabulary building programs. And because of the neuroscience, we've come to appreciate that these children from low SES backgrounds may be different for other reasons. They may be different because of environmental factors. And ultimately, we need to think systematically and structurally about how we maintain safe environments where our children can play and grow. Imagine if your entire life felt like this. We all took an oath to help our patients, and it's not enough to help only some of them. We need to help all of them. And this is one example of how neuroscience can improve patient lives, not just in the future, but today. Thank you.